All right, so today we're diving into something pretty cool.
Yeah.
Robots that can learn complex skills
Oh, wow.
just by analyzing tons of data.
Okay.
Kind of like how we learn. These robots use something called vision language action models,
Okay.
or VLAs.
Right. VLAs, they're, think of it like a robot's brain.
Yeah?
It can process images,
Yeah.
understand written instructions,
Okay.
and then figure out the physical actions
Yeah.
needed to complete a task.
So like if you wanted to teach a robot how to fold laundry,
Uh-huh.
the VLA would be what allows it to make sense of the whole process, right?
Exactly, but there's a catch.
Okay.
Imagine breaking down every tiny movement
Okay.
involved in folding a shirt.
Right.
It'd be a ridiculously long list of instructions.
Okay. I see the problem.
Yeah.
But how do we teach robots these complex actions without overwhelming them with information?
That's where action tokenization comes in.
Okay.
It's like creating a simplified code
Yeah.
to represent those complex movements.
Mm-hmm.
Think of it like translating a robot's smooth motions
Yeah.
into a series of key instructions
Okay.
that a VLA can easily understand.
So it's like giving the robot a cheat sheet for
Exactly.
learning a new skill.
Exactly. Now, traditional methods of action tokenization are
Yeah.
kind of like trying to write a novel
Okay.
using only a few basic letters.
All right.
It works, but it's slow and clunky, especially for fast, intricate actions.
Makes sense. So there has to be a better way to do this, right?
There is, and that's what this deep dive is all about.
Okay.
A new approach called FAST,
Okay.
which stands for Frequency Space Action Sequence Tokenization.
Wow. That's a mouthful.
Yeah, it is.
So, but it sounds like a big deal. What makes FAST so different?
Well, FAST takes inspiration from how we compress images, like using JPEGs.
Oh,
It applies a similar principle to robot actions.
Interesting.
This paper we're looking at today is
Yeah,
really
yeah.
interesting. It talks about compressing the robot's actions
Uh-huh.
before training, like zipping a file on your computer to make it smaller
Yeah.
and easier to work with.
Okay, I'm starting to get the picture, but how does that actually work?
FAST uses something called the discrete cosine transform,
Okay.
or DCT. It's a mathematical tool
Yeah.
that identifies the most important pieces of information
Uh-huh.
within a sequence of movements,
Okay.
kind of like highlighting the key plot points in a novel.
Right.
This lets us discard the unnecessary details
Yeah.
and focus on what's essential for the
Okay.
robot to learn.
So DCT is like finding the greatest hits
Exactly.
of a robot's movement, the essential moves it needs to learn.
Exactly. And by compressing those actions
Uh-huh.
with DCT,
Okay.
FAST makes the learning process
Yeah.
much faster and more efficient.
This paper has a really cool example about how seemingly simple tasks
Right.
can become harder for robots when you increase the speed of the actions.
Yes.
Can you walk me through that?
Sure. Imagine a robot
Okay.
trying to trace a curved line smoothly. As you speed up the required movements,
Yeah.
traditional methods start to struggle.
Okay.
They miss the subtle changes in direction
Mm-hmm.
because they're trying to represent a smooth curve
Right.
with a limited set of clunky instructions.
So it's like trying to draw a perfect circle using only straight lines.
Yes,
The faster you go, the more jagged and inaccurate it gets.
that's a great analogy.
Okay.
But FAST, on the other hand, excels
Yeah.
at handling these high-frequency actions.
Okay.
Figure 3 in the paper really illustrates this difference.
Okay.
You can see how FAST captures the smooth curve beautifully,
Uh-huh.
even at high speeds, while traditional methods produce a choppy mess.
So AFAST helps robots learn complex movements more accurately.
Yes.
And at much faster speeds. That's incredible.
Yeah.
But does this translate
It does.
into real-world skills for robots?
Absolutely. The researchers tested FAST
Okay.
on actual robot tasks like
Yeah.
bussing tables
Wow.
and even folding T-shirts.
Wow. Folding a t-shirt? That's impressive. It always feels like I'm wrestling with an octopus when I try to fold laundry.
I hear you.
What kind of results did they see with these tasks?
The results were pretty remarkable.
Yeah.
FAST not only led to faster learning,
Okay.
but also allowed them to train a robot
Mm-hmm.
using a massive complex data set
Okay.
called Droid.
Wait, a data set called Droid? Is that a coincidence?
Maybe not, but what's really fascinating
Okay.
is that the Droid trained robot
Yeah.
could then use what it learned
Okay.
to navigate new environments
Uh-huh.
it had never encountered before.
So it could adapt.
This means it could generalize its skills, which is a huge step towards
Wow.
robots that can truly operate
Yeah.
in the messy, unpredictable real world.
That's incredible. So we've got robots learning faster,
Yeah.
more accurately, and adapting to new situations.
Mhm.
It sounds like fast really is a game changer.
It is.
But how do we apply this to different types of robots?
Right.
Do we need to create a new fast system for every single robot design?
Well, that's where Fast Plus comes in.
Okay.
It's basically a universal action tokenizer
Uh-huh.
that can be used
Okay.
with a wide range of different robots.
Interesting. So Fast Plus is like a universal language translator
Okay.
that allows robots to understand instructions, no
Okay.
matter how they're built or how they move.
You got it. This means we can train robots much faster
Okay.
and more efficiently,
Right.
regardless of their shape size
Yeah.
or the way they move.
Mhm.
It's a major step towards making robot learning
Okay.
more accessible and practical.
Okay, so far, Fast sounds like a clear winner.
It is.
But I'm curious, how does it stack up against
Yeah.
other cutting-edge approaches, like diffusion models?
That's a great question.
Huh.
The researchers actually compared Fast Plus head-to-head
Yeah.
with diffusion models.
Yeah.
And what they found was really interesting. Well, they discovered that Fast Plus was actually more computationally efficient.
Okay.
This means it needed less processing power
Uh-huh.
and time to get similar or even better results compared to diffusion.
Okay, so less computer power
Yeah,
and faster learning. That's a big win for Fast Plus,
it is.
especially when you think about training robots with those
Right.
massive data sets we were talking about earlier.
Precisely. Those data sets can contain millions, even billions
Wow.
of data points.
Yeah.
So the fact that Fast Plus can achieve
Yeah.
comparable or even better performance while
Right.
being lighter on the computing side
Uh-huh.
is a huge advantage.
That makes a lot of sense. So we've established that Fast is incredibly efficient.
Yeah.
But we were talking about Fast Plus being this
Right.
universal action tokenizer. Can you unpack that a bit more for me?
Absolutely. You see,
Mm-hmm.
traditional methods for
Right.
action tokenization often require a custom approach.
Uh-huh.
For each robot, it's like having to create a whole new language
Wow.
each time you want to communicate with a different robot.
That sounds incredibly tedious.
It is,
Um,
but with Fast Plus, you have a single system that can be applied across a wide range of robots.
Yeah.
Think of it like having a universal remote control
Yeah.
that works with all your devices.
Okay.
It just makes things so much simpler.
So instead of having to reinvent the wheel every time,
Right.
we have this plug-and-play solution for
Right there,
teaching robots new skills.
Exactly.
That's got to be a game changer for the robotics field.
Exactly. It streamlines the development process
Uh-huh.
and makes it much easier to deploy
Okay.
fast-powered robots
Yeah.
in all sorts of real-world situations.
Okay.
This means we can move faster
Yeah.
from the lab to practical applications.
Now, I remember the paper mentioned some really interesting real-world tasks.
Yeah.
They tested using fast, like table bussing and even laundry folding.
Yeah, those are great
So
examples.
those always seem like super complex skills for robots to master.
Those tasks are excellent examples of why fast is so groundbreaking.
Okay.
You see tasks like folding a t-shirt
Right.
or bussing a table
Uh-huh.
require a level of dexterity and adaptability. That has traditionally been very challenging for robots.
Yeah.
They involve grasping, manipulating objects,
Yeah.
sometimes even dealing with unpredictable, deformable materials
Okay.
like fabric.
Yeah, I can't imagine trying to program a robot to deal with a wrinkled shirt
Exactly.
or a wobbly stack of plates.
Exactly. But with FAST, the robots were able to learn these skills
Okay.
through demonstrations.
Uh-huh.
And then, get this, even generalize their skills
Wow.
to handle new situations they hadn't encountered before.
So they could adapt.
Like imagine the robot being able to fold different types of shirts.
Oh, wow.
It's never seen before or clear a table
Okay.
with objects arranged in a new way.
Wow. That's incredibly impressive.
It is.
It's like the robots are actually understanding the task
Yeah,
rather than just blindly following a set of pre-programmed instructions.
that's exactly right.
Mm-hmm.
FAST enables a level of flexibility
Okay.
and adaptability that was previously out of reach for most robots.
Yeah.
And it's a huge step towards robots that can seamlessly integrate
Uh-huh.
into our everyday lives and help us with all sorts of tasks.
So we've covered the efficiency of FAST,
Right.
the versatility of FAST Plus, and its ability to tackle complex real-world tasks.
Yes.
Is there anything else?
Well, there's one more thing
Yeah.
I think is really intriguing.
You were about to tell me about something else that makes FAST stand out, something really intriguing. What is it?
Remember how we talked about FAST being inspired by the way we compress images
Yeah.
with JPEGs?
Yeah.
Well, the researchers behind FAST believe that this principle
Okay.
of efficient representation could have implications far beyond
Okay.
just robotics.
Okay, now that's fascinating. We've been deep diving into how this impacts robots,
Right.
but you're saying this could be a game changer for
Yeah.
other areas of AI and machine learning as well.
Exactly. What if we could apply this same concept of compression
Mm-hmm.
to other types of data,
Uh-huh.
like human language or even complex scientific information?
I'm trying to wrap my head around this. Are you suggesting we could, like, compress a whole textbook into a tiny file?
Well, it's not quite that simple,
Okay.
but the analogy is on the right track.
Okay.
The key idea is that by finding
Yeah.
more efficient ways to represent information,
Mm-hmm.
we can dramatically speed up the learning process.
Okay.
For AI systems, imagine an AI that can absorb and process information
Yeah.
at an incredible rate, just like FAST does
Mm-hmm.
with robot actions.
So instead of feeding an AI massive amounts of raw data,
Right.
we could give it a highly compressed,
Right.
super efficient version that highlights the key insights and patterns.
Exactly.
So like giving it a cheat sheet for understanding the world.
Precisely. This could revolutionize how we train AI models,
Okay.
making them much faster learners
Yeah.
and enabling them to tackle
Yeah.
even more complex problems. Imagine the possibilities
Yeah.
in fields like natural language processing,
Uh-huh.
where AIs could learn languages incredibly quickly, or in scientific research, where AI could analyze huge data sets in a fraction of the time it
Yeah.
takes today.
It's mind-blowing to think about how fast,
It is.
which started as a way to improve robot learning,
Right.
could potentially unlock entirely new levels of efficiency
Yeah.
and understanding across so many different fields.
You really
It really feels like we're on the cusp of something truly groundbreaking.
I completely agree. FAST is not just a step forward.
Mm-hmm.
It's a potential paradigm shift in how we think about AI
Yeah.
and machine learning. By exploring this principle of efficient representation,
Okay.
we might unlock a whole new era of intelligent systems,
Wow.
capable of learning and adapting at speeds we can barely imagine today.
Well, folks, we started this deep dive by exploring how robots can learn
Right.
from massive amounts of data, and we ended up contemplating the future of AI
Yes.
and the very nature of knowledge itself. That's the beauty of the deep dive, isn't it?
It is.
You never know where the journey will take you.
It's been a fascinating exploration, and I can't wait to see what new discoveries emerge as researchers continue to delve into
Yeah.
the principles behind FAST and its implications for the future
Yeah.
of intelligent systems.
Thanks for joining us on this incredible journey. Until next time, keep exploring, keep learning,
Absolutely.
and keep asking those deep questions.